Earth Science Time.
Episode 7, Season 1.
I don't think so. More like, that's not how it goes either. It's like season, still 1 episode, like 40. Anyway, we're going to talk about stream development. So write this on there. Stream development. There's a video you can find elsewhere on YouTube about, if you just type it, I guarantee if you type in the word developers onto YouTube, there's a video of a guy from Microsoft in like 2001 just shouting the word developers over and over again and sweating because of it. It's a good video. Anyway, we're going to talk about stream development, which is about how, guess.
Streams develop.
Yeah, you got it. How streams develop. So once again, we talked about streams in the last video. That's just a moving body of water, and this is going to talk about how they grow and change over time. So, we already talked about stream channels and banks, but now we need to talk about this process called down cutting. So, let's start with this. Give me a couple of, in your mind, the biggest rivers in the world.
Mississippi.
The Mississippi.
Amazon.
Nile. There you go. Thanks, Levi, for all three of them. Okay, so biggest rivers, right? Biggest meaning what? In this case, those three are the three whattest rivers. Longest. They also have, if you've ever seen pictures of them, they happen to be very wide. Okay, but they are not. What's the other property of our discharge? You remember they're not very. They're pretty deep. I would say medium depth, but they're not very fast. They're not very fast. So in general, and you should have this in your brain. I don't know that I necessarily need to write it down, but in general, you should be aware that fast-moving mountain streams, like on steep slopes, those move faster than what we call meandering rivers on plains. So downcutting is the process where fast-moving streams actively erode downward to their base level. So pretty much this. The base level of a stream, when we talk about the base level of a stream, it's the altitude at which it will eventually flow into its next body of water. So for instance, the White River here flows into what body of water?
The Amazon River.
No, well, not between those two. First it flows into the Niobrara, and then that flows into the Missouri. And so the base level of the White River is the altitude at which that flows into the Niobrara. The base level of the Niobrara is the altitude at which that flows into the Missouri. So thinking about just the White River for now, we've got this here in cross-section. This is all going to be in cross-section. Here's where the Niobrara River, good. This is the level at which it will eventually flow into, right? And so there might be this kind of gently sloping, and then it gets a little bit higher the further away we get, right? Because as you know, water in general flows downhill. So where it started, or what we call sometimes the headwaters, and you should write that down. The headwaters is what we call the region in which that river begins, right? The region of the part of its watershed where the river begins is called the headwaters. And so the whole thing here, this altitude, I'm going to try to draw this as a level line. This altitude here is called the base level. And the base level, like I just said, the base level is, oops, I should switch this to picture-in-picture. The base level is the altitude at which it will join up with its distributor, with the river that it flows into, or the stream that it flows into, or the ocean that it flows into, right? And so the higher above the base level it is, the more active downcutting it can do. So when it starts out here, it can actively downcut. So the river flows in this way, right? And it's doing more erosion. The point of this is it does more erosion here when it's high above its base level than here when it's not high above its base level. So if it's moving faster here, what kind of sediments in general can it move?
Sand.
Well, maybe not specifically, but larger sediments, right? Compared to here, it can move larger sediments here. And this is true for all rivers, right? So generally, small streams in mountains, like small streams with a steep slope up near their headwaters, move faster than those on a plain, right? So the White River here in town, when it's on a plain, has kind of spread out. It's what we call a meandering stream. Whereas when it's up in its headwaters, it is actively downcutting. And once again, downcutting is this process where it's doing erosion. And the erosion stuff, right? We talk a lot about how it's moving faster and so it carries more sediment. But you understand, of course, that sediment is coming from the environment, right? So the environment, the stuff that this hill is made out of is going with the river. And then over time, this river gets deeper and deeper and deeper. And look what happens to the slope. The deeper the river gets, the deeper the river downcuts, what happens to the slope that it was on?
It's small.
It gets smaller, so the river starts moving slower. And this right here, where it's, I should have actually circled it. This right here is where we get things like cascades or waterfalls, or where there's whitewater rafting. Is right where it's kind of going into a downward slope is where the water is moving really fast. Okay, so look at this picture on page 232. The whole thing, the river is downcutting, and at this point, like I just said, this point where it's starting to go down a steep slope, this is engaging in what's called headward erosion. Headward, like Edward. Headward. It's called headward erosion, meaning it's moving towards the what? The headwater, right? It's moving towards the headwater. And this right here, where the headward erosion is occurring, is where we get, like I said, waterfalls. That's where canyons are formed, is at the headward erosion. So Niagara Falls, are you aware of the existence of Niagara Falls?
Yeah.
Yeah, Niagara Falls is the place where headward erosion is occurring on that river. I forget even what river it is, but it's basically in between Lake. Now I'm going to say something stupid. One of the Great Lakes and another one of the Great Lakes. I don't know what river it's on, though. And by the way, if we look at this at the other cross-section, right, we're looking at it this way, but if we look at it the other way, what shape of valley is it forming as it does this?
V.
Let's all say the right answer.
V.
V. It's forming a V-shaped valley, right? Because just like we saw it in the video yesterday, so when it started out, maybe it's just like that, right? And then as this headward erosion occurs, right, it gets deeper, it downcuts, and eventually it gets like this. So you're aware, okay, so maybe you've watered a garden or something, or you've played with sand at the beach, and you're aware that if you dig a straight-sided trough, with your hand through the water, right, these walls can't support their own weight because of the angle of repose, right, and so they collapse. And that's why this becomes a V-shaped valley. Because as it cuts down, it cuts straight down, but the walls collapse in on themselves, and so it forms this V shape. Bueno?
Stronger.
What?
Which is stronger?
Yeah, the V shape, the angle of this V-shaped valley matches the angle of repose of the sediment this is made out of, right? And so if it's a very strong, it doesn't even have to be sediment, if it's a very strong material, like marble or granite or something, my name tag. If it's a very strong material, like an igneous or metamorphic rock, the valley's walls might be very steep, right? If it's a pretty loosely held together material like gravel or just loose sand, it'll have a very shallow angle of repose, right? So it'll have a very shallow V. Okay, this is all about downcutting. These are up high mountain rivers. Not necessarily mountain, but steeply sloped rivers that are moving very fast, right? So they're generally thin, they have a small width, right? They're normally fairly shallow, so they have a small depth, but they have a quick speed. And the speed is what determines, even if they have a small discharge, right? Because remember, discharge was depth times width times speed. So even if they have a small depth and a small width, the speed allows them to carry larger sediments. So even if they have a small discharge, they can still carry large sediments. I'm going to erase this real quick. So this was about, oh, this is not working so hot. This looks great.
You're just gonna have to spray it.
I think this looks really good, actually. Okay, anyway, while I'm doing this, you write down the next thing we're going to talk about, which is meandering streams. Meandering. This is kind of how you guys live your life. You just meander from place to place, right? You slowly. Yeah, what is that supposed to mean? What's meander mean? What does it mean to meander?
It's kind of
Like a turtle.
go off track.
Slowly go off track. Yeah, those are. I think those are definitely true about how some of us choose to live our lives. Yeah, and also it's true about, we're going to talk about meandering streams, right? So go off track. That makes it sound like they have a designated path, but what it basically means is they're straying away from just a straight line, right? So if you live your life on the straight and narrow, then you're not meandering. Yeah, sure. It is for your life, but we're going to talk about meandering streams. Meandering streams. So now we're going to look at this from a map view. So remember, cross-sectional view is when we're looking at things like, kind of like cut in half from the side, and now in map view we're going to look at it from the top. So here's a river or a stream. So I'm looking at the top view of this. And just because I didn't draw them perfectly straight, which was kind of deliberate, but also it's kind of difficult to draw a straight line, because I didn't draw it perfectly straight, it's got some curves in it, right? There's no such thing as a perfectly straight river. A perfectly straight river would never meander, but that doesn't ever happen. And now here's the thing you have to understand about water. It seems maybe in your head that you feel like if you were a water molecule moving along this river, you would just drive along it like you drive along the highway, like you want to stay in between the lines, right? Which I tried to do here.
That doesn't look like you stayed in between
There.
the lines.
Well, let's start out with the river shaped a little bit more curvedly like that. And then you might think, I'm a water molecule, I'm just going to stay right in between the lines. But that's not what water molecules do, because they, unlike you, can't think. And so they just move because of inertia, because of Newton's first law, right? They just move in a perfectly straight line no matter how close they get to the side, right? You see what I mean? So instead of moving around a curve, they just bump into the curve. Okay? And that's extremely important because when they bump into the curve, they probably do what?
Bounce up.
And when I say they you mean, I mean what? What is they in this case? Shh.
Water molecule.
Yeah, the water molecule. So when they bump into the side of the stream, they do some erosion. And so basically these spots where the water molecules are hitting more frequently get eroded faster. And so the stream starts to curve that direction. Should be drawing another curve in here. There we go. Nice. And so it gets more and more curved as time goes on because the water molecules are bumping into this, what's called the cut bank. The outside edge of a curve is called the cut bank.
You always want to take the inside.
And at the cut bank, what's happening is erosion. The cut bank is on the outside of a curve, and that's where erosion is occurring. Because why? Why would erosion be occurring there more than in the middle of the stream?
Because nothing's going to hit it.
Okay, yeah, and because the water comparatively is moving faster on this edge than on this. So look, a lot of this is from page 235 if you look. So the stream has this channel. It's looking at, you can see the stream channel there on 235, right? When it's going straight down the river, its maximum velocity is in the center. When it's going around a curve, the maximum velocity is near the outside of the curve, like I just said, the cut bank. So more erosion occurs at the cut bank, so this angle, this curve gets steeper and steeper and steeper. So if the cut bank, the outside corner, is having active erosion, what's probably happening on the inside corner? In fact, even the opposite. If it's going slower, what would probably be happening? Deposition. Yeah, so deposition. So here the inside of the curve is called the point bar. Are you writing these things down? The point bar, and this is where deposition occurs. So basically, the water is moving faster on the outside of the curve and slower on the inside. And because of that, erosion occurs on the outside of the curve and deposition occurs on the inside. And so instead of getting straighter and straighter as time goes on, meandering rivers always get curvier and curvier and curvier.
Wow.
And then something kind of interesting happens. If it gets really, really curvy, we start to get this little thing here. And eventually what's going to happen, you can see, if this gets any curvier, what's it going to do? It's going to hook up. They're going to connect, right? They're going to connect, and then the water's going to be like, well, I'm going to go this way. Because remember, water's always going the easiest way downhill. So the water's going to go through here instead. And this whole thing here kind of gets cut off. And this is called an Oxbow Lake. In places that have really broad, flat landscapes with not much feature, kind of like in the middle south of North America, you know, like somewhere like Tennessee, Arkansas, Alabama, that kind of region, Mississippi, eastern Mississippi, there's a lot of these Oxbow Lakes where what's basically happened is a river has gotten so meandery that one curve of the river has hooked up with another one, and it leaves this Oxbow Lake over here all by itself, just hanging out.
Whack.
Wiggity whack, that's right. Oxbow Lake forms because the edges of a meander cut up or hook up with each other, yeah, and then the water follows that path instead. So in this way, the river can get straighter, but only by connecting and then forming an Oxbow Lake where the curve is completely cut off, right? So it's kind of an active process where most of the time the river is getting curvier and curvier and curvier until it gets to a certain point, and then suddenly it gets much straighter. Do you have questions about... So I'm going to expect you to know cut bank, point bar, and Oxbow Lake and how each of those things form and why. Is that... You got that pretty good? Okay. Let's move on to the next thing real quick. I think let's talk about two more things. Nope, we're gonna talk two more things. So, and they're the same idea, except they happen in different circumstances. So, in general, what happens when the stream slows down? The sediments are deposited. What might cause the stream to slow down besides what we just talked about?
Loss of energy.
Loss of energy. Yeah. Well, so when might it lose energy? Two major things can happen. If the what decreases, if the slope decreases, right? If it goes out onto a plane, right? Or if what other thing happens?
It flows into another body of water.
Specifically, what kind of body of water?
Lake.
Probably a lake or an ocean, right? So, let's just put this river onto. Let's use actual English though. River flowing onto an open plain, and we're going to have over here river flowing into still body of water. It doesn't have to be perfectly still, obviously, but into something that's relatively still. When I say still body of water, I mean what two things generally?
Lake and ocean.
Lake and ocean. So if the river flows onto a plain, it's going to dump all of its sediments right away. So here's river flowing, and then if there's a plain here, it's just going to form this shape, and all the sediments are going to be in that. And it's going to be fairly poorly sorted. And we call it an alluvial fan. This is what forms in the alley behind my house because it's sloped. Every single time there's rain, the whole dang alley washes down into the road, right? The road is flat in front of my house, and the alley is curved. And so every time it rains, all the sediment from the alley, which is not paved, washes on to that, and it forms this alluvial fan.
Do you know money?
Poorly what?
Poorly sorted, meaning it's all different size sediments. So when a river, right, there's not a river in my alley, but when it rains there kind of is. When a river carrying sediment flows onto a plain, it just deposits all that sediment instantly, and it forms this fan shape.
Poorly sorted and...
It's called an alluvial fan. Alluvial fan. The same thing kind of happens when, and you've heard of this before, so here we have a lake or an ocean. What do we call this area where all these sediments are deposited? You know what this is called. I think you've probably talked about it in geography.
Beach?
A delta. This is called a delta. And delta deposits, because it's going into water instead of on the land, they are well sorted. But what's going to get deposited closest here? As it loses energy, what's going to get deposited first?
Bigger sediments.
Pebbles. Maybe not necessarily pebbles, but the biggest sediments are going to get deposited first. So we're going to have the biggest sediments here, then smaller sediments, then even smaller sediments out here, right? So what's going to flow the farthest? The smallest sediments.
Clay or silt.
And as this builds up over time, right? As these pebbles build up a new little perch for the river to be on. If we look at this is map view still. If we look at this from the side, the delta in cross section, what are we going to see? So we're going to see where the river was, where pebbles were deposited. Oops, sorry. Let's change it. Let's start with sand. Where the sand was deposited, and then as the river moves out, what's going to be deposited on top of that? Pebbles.
Oh, my bad.
Pebbles. And so here, where there were pebbles, right? So we get this sequence in here where there was previously silt. There's going to be what deposited on it? Try again. Sand is going to be deposited on that, and then on top of that is pebbles. And so if we look at this sequence here, we get that it's doing what? What's it doing as it goes up?
It gets bigger.
Yeah, and we call this a coarsening upward sequence. A coarsening upward sequence. Right? So if we see a deposit where there's small sediments on the bottom and larger sediments on top, we can think to ourselves, oh, a delta was here. And I hope that's the point of all of this, right? The whole reason we learn about any of this is so that when you go out into the wild and you see a rock outcrop and you see this, or you see poorly sorted sediment, you can tell what caused it to be there, right? Why that is powerful is because you can go to a place and tell what the past was like just by looking at the sediments, right? You can tell there's not a river here now, but I know there used to be because I can see this. You see why that's important? That's what the videos that we watch are all about, is how we can use this evidence to tell how the world used to be. Questions? Do your homework.